Ah. Who is this? Vexihun. Who is that? Man. Oh, tropical. Tropical. Coming in with the teacher's pet. Wow. Awesome, Vex. Awesome. Ah, wow, incredible. Oh, Monday you reserved it? Oh, you reserved it. Okay, I see. That's cool. That's great. What am I teaching today? Oh God. That. And then that. Huh. Okay. All right. Oof. Crow! Hey, what's up, Crow? What's going on? Oh, you did? Oh, I hope it went okay. Oh no. Oh no. Alright, let's just forget about it and move on with life. That's always a good strategy. Okay. So what do I have to do? I gotta put this music on. And class, come on in to my 45-minute lectures. we are what? Oh, it says it right there. October 26th. That roughly gives us about a month, a little bit more than a month left in the semester. And so it's about time that we started moving away from group theory and starting to make the transition to the next topic. Vex, do you mean like fields of rational functions, like that? Fields of rational functions? Then yeah, we'll have Galois theory next semester. So if that's what you mean, then we will have that kind of stuff happening next semester. Okay, so yeah, but in order to get there, we need to discuss the next topic, which is rings. Yeah, maybe not Vex. I mean, we'll have just the basic definitions of and examples this semester, but nothing interesting will happen for a while. Okay, so and also, class, you should understand that the group theory is winding down for now. Group theory never takes a break. It's kind of everywhere at all times in all parts of mathematics. So just our focus on just raw group theory is gonna shift. Okay. It'll come back. It'll be back with a vengeance in second semester. We still have a lot to learn about just pure group theory, but it'll only make sense. That more sophisticated stuff will only make sense in the context of Galois theory, where there'll be a need for it. Okay. So what I'm going to do today, as one of the sort of ending group theory type classes, is I'm going to give you just... Why did we call that one theorem back in the day the first isomorphism theorem? It's because it comes in a package of 3. And so I might as well show you those as we depart. And then there are some things I owe you, very basic things. Like, I've never actually told you what it means to have a subgroup generated by blank, or the phrase generated by. It's probably a good idea that you see what that means quite clearly in an algebra class, because the phrase generated by is used all the time. And you might think you know what it means, but maybe your definition is not so rigorous. And so I'll show you the clean way to define the concept of generated by. Okay, so let's begin that. Let me tell you what the second and third isomorphism theorems are about. Okay, so the first thing I'll tell you is that these theorems are used in, like, buried deep inside of arguments. Okay, so you're not going to see such easy knockdown examples of the use of a second or third isomorphism theorem. They're kind of they're technical. These are technical tools. All right, so it's gonna feel a little bit dry, but the setting of these two things is kind of undeniably general. So the point of these theorems is to give you is to prove a general fact about certain situations that arise in, well, they'll definitely arise in Galois theory, but in general, in group theory in general, when you're trying to do more sophisticated things. So let me talk about that situation. So all the isomorphism theorems, you know, the ones with names, they all date back to Emmy Noether, who is quite famous. Famously, probably one of the first female great mathematicians, Emmy Noether. So she's the first one who really like isolated this kind of isolated the abstract essence of the following type of situation. So all these isomorphism theorems involve the following setting. You'll have a normal subgroup. Maybe I should keep the normal subgroup to be K. Let's do K. Okay, so you'll always have a normal subgroup in here, in the setting. And the first isomorphism theorem kind of had a normal subgroup floating around, namely the kernel of a homomorphism. So you have a normal subgroup, and then you're going to have another subgroup, sort of a friend. And then a plus friend. And the second and third isomorphism theorem will tell us like some general facts that are true in this context. That it's a very general situation. So you have a normal subgroup and then another subgroup. It might be normal, it might not be. All right, so let me tell you what the second isomorphism theorem says in this situation. It states that there is a natural isomorphism between the following two groups. You take this arbitrary friend subgroup, modulo this subgroup. Notice that, okay, I'll talk about. These two groups are isomorphic. This quotient and the following quotient. Okay, so I need to explain. Oh, thank you, Micah. Thank you, I am not. Thank you, Gela, and each and every one of you. All right. So what is? Let's unravel this. Make sure everything parses. Okay. So notice that H intersect K is normal. Okay. Go ahead and do that quick, just simple exercise. H intersect K is a normal subgroup in H. Okay, good. I'm not saying it's a normal subgroup of G or anything. No, just in H. As a subgroup of H, it's normal. So that makes sense. Left-hand side makes sense. What makes the right-hand side make sense? The right-hand side, notice that H times K. This is just the set of products. Little h's times little k's. That's usually just a set. A weird subset of a group. But it's better than that when one of the groups is normal. Okay, this thing is a subgroup. Because K is normal. This is that other way of interpreting normality, which is that, you know, if you're doing some math, then normality allows you to trade like an element in K times an arbitrary element with the other element. You know, you can swap across, except the K part might get changed. So this part, you can swap them with an asterisk. this is equal to h2 times k1 prime times k2 times h1. You see that? That's the fact that you can trade off for another thing in k. That's just another way of talking about expressing the normality condition. And so this is still in h times k. So the product of two things in that set is still in the set. This is what's allowing us to think about hk as a group, subgroup. And obviously h times k contains k. And k is normal. K is normal in everything. Once it's normal in G, it's normal in any group that contains it inside of G. So this side makes sense. So now it makes sense. And all the second isomorphism theorem is saying is that this is the relationship between among all these groups. All right? So another way you'll see the second isomorphism theorem sort of expressed is like this. So you might also see it as the Diamond Lemma. Okay, so, or the word diamond might be used. And the reason is this. You have H and you have this normal K. In that way, out of those two things, you get four different groups, subgroups of G. You've got H, you've got K, you've got their intersection, and you've got their product. Product meaning set of products. Okay? And there's like inclusions. There's obvious inclusions. And the Diamond Lemma is saying that this quotient is naturally isomorphic to this quotient. Wait, there's two. Oh yeah, there's two kappas in the chat. Oh no. Oh no. Okay, so you might see this diamond type shape. In fact, class, it's actually quite useful to draw these kinds of these kinds of inclusions of groups when you've got several bouncing around in an argument. It helps you like keep track of like index math. Like sometimes it's useful in practice to put little numbers here. I don't know, indicating the index of this group and that group and so on. It helps you just kind of keep track of how the groups are situated relative to each other. This is called producing a lattice of subgroups, kind of a diagram of inclusions and arranging them so that they kind of make visual sense in the brain. But this is the reason why you might see it called the Diamond Lemma. Okay, let's look at the proof of the second isomorphism theorem. What's the point of it? The point is this, that it relates all four of these groups. It tells you a relationship among all four of the groups. Okay, so proof of the second isomorphism theorem. All right, so what you do is you exhibit a homomorphism. And it's easiest to go, yeah, from H to okay, so let me tell you what this, I mean, you can't just draw an arrow and say this is a homomorphism. You have to say what it is, right? It's defined by an element H gets sent to. The symbol for maps to, like an element goes to, is an arrow with a little bit of a feather. I don't know. Okay, H goes to what you write is this coset. Notice this is H times all the elements in normal subgroup. That's a coset. This is an element. Please notice that. It's kind of obvious. It's a coset of K inside of HK. Little h is in capital H. Great. So this is an element. And that's the homomorphism. Why is it a homomorphism? Well, let's do it like this. Okay. What is phi of A times B? A and B are both in H. Well, it's by definition AB times K. It's this coset. But K is normal. So coset multiplication works the way you want it to work. Okay? And so this is normality. Okay, so that's your simple kind of one-liner reason why it's a homomorphism. Great. And now step 2, ask what the kernel is. Okay, let me write this out for you. By definition, the kernel of phi is the set of elements in H such that H times K is K. Oh, maybe it's too fast. Phi of H is the identity element. I denoted it by ID inside of here. But what's the identity coset? K itself. What phi of H is, this coset is the identity coset. But a left coset is the trivial coset if and only if what you're lefting by is in the group. So this is but if you stare at this, it's the elements in H that are also in K. That's the intersection. Okay? So the kernel of phi is the intersection of the two groups you started with. Oh, girl. Thank you. Welcome. I wonder how many of these are bots. Wait, 1024. That's an auspicious number. Oh, yeah. Hello, hello, hello. Well, come on in. I taught Calc 3, I guess? I don't know what I taught, Kappa. It was Calc 3, I think. Okay, so, class, I think you know what's going to happen now. I exhibited a homomorphism. I identified the kernel. So, by the first isomorphism theorem, phi factors through H mod HK, i.e. You get an induced mapping homomorphism which is this is injective. This is injective. All right. Let me say it another way. So you get a diagram. That's the quotient map. There exists a phi bar like this, which makes these functions commute. So it's saying that you get an induced homomorphism from the quotient mod the kernel to the image of the original homomorphism. H mod A, this thing is an isomorphism onto the image of the original map phi. All right. But hey, what's the image of the original map phi? Okay, so step 4. Just a last step. What's the image? The answer is everything. Because after all, what is an arbitrary element of HK mod K? Is a coset of the form, you know, little h times a little k. I just took an element in the big group times the coset k. But look, little k times capital K is the same set, capital K. So it's just saying every coset is a little h times the coset times the group K. Okay, but that's phi of that element by definition. Okay? So every coset is hit by the map. And so altogether, H mod H intersect K is isomorphic to, all right, basically by the first isomorphism theorem. Awesome. So there's your second isomorphism theorem. And good note to yourself, Smash Time. You might want to keep that to yourself next time. You know, a true magician doesn't reveal their secrets, right? Just keep the internal monologue inside Smash Time. Appreciate it. Appreciate it. Okay, Diamond Lemma is done, all right? But I would think of it as this. The relationship among 4 groups that naturally arise when we have our situation. Remember, one of these, this thing is is assumed to be normal in the ambient group G that we're working in. Okay, so that's a basic relationship among these 4 groups. It's a relationship about quotients. Great. The next thing I'll do is I'll just tell you the third isomorphism theorem, and I ask you to try to prove it yourself by exhibiting a particular homomorphism and looking at its kernel. It's the same kind of idea, but I think I should let you try it instead of me just boringly writing it out. Okay, so the third isomorphism theorem. This is the second thing. Confusingly, this is the second thing I wanted to talk about today. Class, don't get confused. Just think of it as the third thing I'm talking about today. Okay, what's the situation? It's just a general fact about a particular situation that happens in life. Here's a situation. Okay. What you've got is what to denote them by. I'll do H and K again, but please notice that it's a more special situation. K is a normal subgroup, and so is H. Two normal subgroups, now nested. All right, so now in the last one, there was no assumption on how H and K were overlapping or anything. Now we've got a nested sequence. Pay attention. Both are normal in the big group. It's not the same as just, I'm not saying this. These are not the same. These are not the same statement. Both are normal in the ambient group, and one is contained in the other. Okay, this is a warning. So that's the situation. And the third isomorphism theorem tells us something about the relationship between some quotient groups. Okay, so the statement is, there is a very natural isomorphism between two groups. Ready? Okay. One of the groups, I gotta make sure I have it in my mind. One of the groups is, okay, it's just it's fractions. Okay. You take G mod the biggest, H is the smallest. K is the middle. Okay, so G mod the smallest. That's a group because that's part of our H is normal in G. Now that group contains a subgroup called K mod H. I'll talk about this, don't worry. It looks horrendous, but you have this is gonna, the left side's gonna make sense in a second. And there is an isomorphism of groups with simply this quotient. In other words, you can like clear out the denominator. That's how you can think of it. Yeah, you can just clear out the denominator. Okay. I don't have to explain why the right-hand side makes sense as a group. I think I should probably say a word about why the left-hand side makes sense as a group. So look. Take a look at G mod H. What is G mod H? It's the group of cosets, right? So inside of G mod H, you can look at the set of cosets, which are like K times H's, as K varies in the intermediate group. Okay? You can just look at those cosets and notice that those cosets with the multiplication of just coset multiplication, which works because everything in sight is a normal subgroup. H in particular is a normal subgroup. That subgroup is like equal, just exactly equal to K mod H. So K mod H is a subgroup of G mod H. And here's the thing. K mod H is normal in G mod H because K is normal in G. So I want you to realize, very simple, that this is actually a normal subgroup. So because remember, K is normal in G. Okay, so go ahead and do some check normality. Okay, so now the left-hand side makes sense. It's a group. This thing is normal in here, so I can take this big fraction bar. All right? And the third isomorphism theorem saying that there is an isomorphism between that complicated nested quotient and this one. It works like fractions, in other words. Okay, so I'm not going to show you the proof of this because the proof is similar. Except you begin with a very, very easy to write homomorphism from G mod H to G mod K, which is surjective. Go ahead and try to come up with a homomorphism. Very simple-minded. Got to check it's well-defined, but simple-minded homomorphism that goes like this, and then go through the same kind of reasoning as with the second isomorphism theorem. I trust you in doing this. Okay, great. Those are just loose ends. If you learn a theorem called first isomorphism theorem, and then your instructor doesn't tell you that there are two more in the package deal, it feels like you didn't learn the full thing. But you won't see the exact use of that general machinery until probably next semester. Okay? Or maybe I'll use it when I try to talk more about 168. I might use one of them. I think I actually will. I think I might use the second isomorphism theorem in the middle there. All right, but forget about it. It's a general fact about certain situations. Let's move on to the thing the vocabulary that I owe you. So I owe you some vocabulary. And it's very embarrassing that I never taught you this before in my 45-minute lectures. Okay, so I need to tell you what generated by means. What does the phrase okay, so I know you might have an idea of what it means, but if you're anything like I was when I first approached this stuff, I had that idea, but the idea was a little bit not precise. Okay, so let me tell you what the situation is. So suppose you have a group G, and then suppose you just have a subset. Not a subgroup, just some elements. Finite, infinitely many, I don't know. Just some subset. Okay. The question is, what do we mean by the subgroup generated by S? Okay, I know that for some of you, I'm only talking to newcomers. Old people, why are you here? I don't get it. Okay, you might have in your mind an idea. Oh, I know what it is. Take every element in S and multiply them. Okay, I get more stuff. Good. Now, take those things, multiply them one at a time with the old things. Oh, also put inverses every time a new element is born. Like this. And you grow, multiply. Oh, but then at each step, multiply with everything before and inverse. Oh, I know what you mean. I know you know what you're thinking. And that's right. Intuitively, that's what we're doing. We're growing a group. And you don't want to, at any stage, add in some element from outside that didn't already deserve to be in it. You kind of want to do it as conservatively as possible. Yeah, that's just BS word salad. I mean, I did a good job of making it sound confusing, and it's because it's not rigorous. Okay, so I'm going to show you the secret. Every time in algebra, generated by, the phrase generated by comes up, there is a slick, cool way to say what you mean. All right, so here's the slick way of saying what you actually mean. Here's how the cool kids do it. The first thing they observe is that the intersection of arbitrary many subgroups is again a subgroup. If you have an arbitrary number indexed by a random set, A, okay, if you have arbitrary collection of subgroups of a group, then the intersection is again a subgroup. Okay, that's the first thing you observe. Class, go prove this. Take any two elements in the intersection, multiply them. Why is it again in the intersection? Because each of the H alphas are... Okay, you can even write it with that tone because it's boring. All right, number 2. Now what do? Consider the following set. Okay? It's the collection of subgroups. So this is, I'll call this script S. Just to be fancy. It's the collection of subgroups which contain the set S. A subgroup, either it has the whole set S in it or it doesn't. If it has it, the whole set, it's an element. It's a member of this exclusive club, script S. Number 3. What is the subgroup generated by S? Answer. It is the intersection over all groups in the exclusive club. You intersect all conceivable groups, subgroups that contain that set. That's what we mean by the subgroup generated by the set. This is the answer. Okay? Why is this a reasonable definition? So here's exercise for you. It's an exercise in set theory, like just sets. Okay. Prove. If K is any subgroup which contains S, and if K is any subgroup that has these first elements that you wanted to create a group out of, then, let's give this a name. Let's give this a name bracket S. Subgroup generated by the set. That's what we will denote it, okay? Then, this subgroup is contained in K. Prove this. Go ahead and prove this, like, right now. Go ahead and try to prove it. All right? But what is it saying? What is this exercise saying? It is saying that the subgroup generated by S is the smallest subgroup which contains S. It is the smallest subgroup imaginable which contains the elements of S. And that's what we want out of the subgroup generated by a particular set. Okay, so that's what generated by means. What is the subgroup generated by a set? Yes, it's what you think it is. Oh, just keep adding in only the elements that are born. How do you make sense of that? Well, this is how the cool kids do it. You take the intersection of all groups containing the set. And this idea is universal. You're going to see it all over algebra throughout your career. So that's why I'm introducing it like this. And I hope it makes sense. Okay, so now you all understand what it means. Bunch of phrases that maybe you didn't understand before, like what the following phrase means. It's like, oh, so G is generated by the elements A, B, X, Y, theta, whatever. Maybe in some sentences you saw some proof somewhere, you saw some sentence like that. Now you know what it means. It's generated by that set. The subgroup generated by that set is the whole group. That's what they're saying. Okay, you'll also see other things like suppose G is finitely generated. Group. You might see some phrase like this. What does that mean? It means there is a finite subset. Just a subset, such that the subgroup generated by it is the whole group. All right? Okay. Thing generated. Absolutely need to know that when you move forward in life. And I'm glad that I was able to end the lecture with that. Okay, so now let me look at chat and let me tell the class that officially, what I'm going to do officially at this point is move away from group theory into ring theory. And let's start talking about the next class of algebraic structures. It's exciting. I think it's going to be easier, to be honest, class. But I don't want to put my biases onto you. But to me, it's an easier topic. Less juice. Okay? But it's essential that we learn the definitions and so on. The rings next. And then after that, the last part of the semester will be fields. Fields are just special kinds of rings. So that's why we do it in this order. Okay? And then all of next semester is the study of fields. But the study of fields involves groups and rings, obviously. Okay, so that's the plan. That's what algebra feels like for this year. Okay, let me look at the chat and see what kind of things. First time in my life I've ever been one of the cool kids. Yes. Will is definitely one of the cool kids. Of course, algebraically challenged. Yeah. Okay, Skuggut. Welcome back. Haven't seen you in a while. Sanbu. Thanks for following. User plus number. Okay, folks. Oh, let's just start the credits. Let's put the credits. Credits. Because of there's so much group theory happening. The G's just flow straight from the pen. So credits. Do the credits. Okay, so there's tropical today. Took the teacher's pet. Tropical. All right, there's Crow. Thank you, Martin. Martin just decided, you know what? I have to follow right now because that's the only way I'll get into the credits. That's right, that's right. Yeah, that's not enough, Martin. You have to say stuff, you have to engage, and so on. Okay, so go ahead and unfollow. All right. No, I'm just kidding. I'll put you in here, Martin. Okay, who else? Okay, we have some moderators here. The moderators, they have to deal with the sort of, you know, the masses. They have to keep them in line. And we've got stand-up comedian Smash Time Fools. Also, he's mainly a stand-up comedian, but he has a side gig of being studying dynamical systems and complex complex analysis. You know, fractals. He has a side gig, but mainly he's a comedian. All right. Then there's BPS, of course. Who else was here? Yeah. Okay. Then there are some new people that I've never heard of. Okay, then there's Vexy. New. And then there's old people. The various kappas. I don't even know. Maybe there's only one kappa. Who knows? And we've got all the students. RDL, AI, Sloth. Old student. Not really a student anymore. I mean. Okay. He knows how to generate. He knows how to generate. And so does everyone else now. All right? So probably in this credit, the last person... Great mathematician Emmy Noether for really just revolutionizing the study of algebraic structures, period. So I think that's a good place to end the credits. Class, go and just play around with that definition of group generated by. Take your favorite couple elements in your favorite group and see if you can figure out the group generated by it, by that set of elements. It's kind of hard, but at least you'll appreciate the slickness of the definition. All right. Awesome. What a great rolling credits. Nice and continuous. Oh, wow. Okay, I gotta go learn calculus. Oh, you wanted to be in? Okay, fine. I'll just put Skugget in there. Oh, no? Okay. Oh man. Okay. Bye bye. See you all later.